Welcome back to the video series on integration and differential equations. In this video, we're going to talk about solutions of differential equations. In our example today, we're going to consider our very first differential equation, and let's start by defining a differential equation. A differential equation, or DE for short, is an equation involving at least one derivative. We can see in our example we've got an equation that involves both the second and the first derivative of y, so that's definitely a DE. And just to give you a bit more context here, y is a function of x. So when we look at this differential equation here, when we think about solving it, we'd be asking whether there's a function y out there that has the property that its second derivative minus 3 times its first derivative minus 4 times itself equals 0. So let's explore this a little bit more in the course of our example. Part A, we want to confirm that the following function y solves the DE, and C1 and C2 represent any real numbers. Intuitively, what we want to do here is plug our function y into the DE and just check that it works. So in order to do that, first thing we're going to need to do is prepare our ingredients. So I'm going to copy y down again just for clarity. And the idea is that we're going to need to figure out y prime and y double prime so that we can check whether this function works. Okay, so y prime. Taking the derivative of the exponential, we're going to get the derivative of the exponent, which is -1. That's going to come down in front. C1 is our coefficient, so that's staying in place, and then we're getting a copy of the exponential. So negative C1 e to the minus x for the first term, for the second term plus 4c2 e to the 4x. Okay, if we try the second derivative, our coefficient is now back to +1, so it's going to be 1 times our original coefficient, c1, times e to the minus x, plus 16 c2 e to the 4x. Okay. So now we're going to plug these ingredients into the DE, and we're going to check that they satisfy the DE. So the way we're going to do that is we're going to compare the left side of the DE to the right side of the DE. Good general rule here is that you want to start with the more complicated side of the DE. In this case, the left side is definitely more complicated, so we'll start with that. We've got y double prime minus 3y prime minus 4y. There's our y double prime. I put brackets around that for clarity. Then we're going to subtract off 3 times y prime. And then minus 4y. Next step, let's expand everything out. So I've expanded out here, and we've just been careful about the signs. So for example, our last couple of terms, we've got minus 4c1 e to the minus x, and then minus 4c2 e to the 4x. So there we go. Now we're going to be able to collect like terms and simplify this. So let's look for all the terms that have the form c1 e to the minus x. We've got 1 of them here. We've got another 3 of them here. And then we've got minus 4 of them here. So overall 0 c1 e to the minus x. And if we do the same thing for the c2 e to the 4x terms, let's count how many we've got. We've got 16 minus 12 minus 4 is 0. So 0, c2, e to the 4x. In other words, that entire left side just simplifies to 0. Then once we've got that simplified, we want to compare that to the right side of the DE. So going back to our original DE here in the question, the right side was 0. And we're looking at this and we're saying, yes, left side equals right side. So that is what guarantees us that this function y that we started with here, this guy here, does solve our DE, meaning it's a solution. So we're sticking with this same DE as we had at the beginning, and in part B now we're going to confirm that the function y equal x squared is not a solution to the DE. So first thing we'll do, let's prepare our ingredients. We're going to need y, y prime, and y double prime. So the function y that we're testing is x squared, y prime would be 2x, and y double prime would be 2. So now let's go through the check. We'll start with the left side of the DE because that's the more complicated one. And the left side of our DE, here it is, y double prime minus 3y prime minus 4y. So let's plug our function in there and we'll simplify this. So we'd have 2 minus 3 times 2x minus 4 times x squared, just by plugging our ingredients into the left side of the DE. So if we were to simplify that, that would give 2 minus 6x minus 4x squared. All right, now let's compare that to the right side of the DE, and the right side of the DE is 0. Now when we're comparing the two sides of the DE, these two sides must be identically equal, meaning we need them to match up not just for some values of x, but we need them to match up for every single value of x. So in looking at the left side and the right side here, we'd say, no, the left side is not equal to the right side, meaning y equals x squared, this function that we started with, that is not a solution to the DE. So it's important to keep in mind when you're presented with a DE, most functions out there are not going to solve the DE, and only a few relatively special functions are going to solve that DE. Part C, we want to know whether this function y here is the general solution of the DE. So to answer that question, we need to ask whether the order of the DE is equal to the number of unknown constants in the solution. And I put the question mark here because we are investigating this question. All right, so let's think about the order of the DE. By definition, that's the order of the highest derivative in the DE. So if we look back at our DE, we've got a first derivative, we've got a second derivative. The highest derivative is the second derivative. So the order of the highest derivative, that would be 2. If your DE just had a first derivative, then your order would be 1. If you had a third derivative in there, the order would be 3, etc. So in this case, the order is 2. Now let's compare that to the number of unknown constants in the solution. So here's our solution here. The unknown constants are C1 and C2, so the number of unknown constants is 2. So we're asking, is the order equal to the number of unknown constants? Yes. So the answer to the question, is this the general solution of the DE? Yes, it is. We have the correct number of unknown constants in the solution. That number matches the order of the highest derivative. Final part, we're going to list 5 particular solutions to the DE. So to get a particular solution, we're going to be looking back up at our general solution. So here it is. And to create a particular solution, we're going to replace at least one unknown constant with a real number. So notice we say at least one. So we can replace both of the unknown constants, or we can replace just one of them with a real number. All right, let's go through and generate some particular solutions. So just for clarity, I've removed some of our work from part C, and I've just put a star beside this general solution so that we can look back up at it. All right, so probably the simplest particular solution, we could let C1 and C2 both be 0, and we'd have the particular solution y equals 0. Next simplest thing we could do, maybe we could let C1 equal 1 and C2 equal 0. So that would give us the solution y equals e to the negative x. We could do that the other way around. Let's let C1 be 0 and C2 be 1. We'd have the particular solution e to the 4x. Okay, and remember that these unknown constants can take on any real number. So if I was trying to be difficult, I could let C1 be pi, for example, and I could let C2 be root 3 over 2, or even a negative root 3 over 2 might be more interesting. So negative root 3 over 2 times e to the 4x. So that would be another particular solution. Okay, but more subtly, remember that we're allowed to replace at least one unknown constant with a real number. So meaning we could replace just one of those unknown constants. I could keep C1 in place and let C2 be 0. Or I could keep C1 in place and I could let C2 be, say, 7. So that would give us another particular solution. And similarly, we could do that the other way around. We could plug in a value for C1 and we could keep the C2 in place. And that's still considered to be a particular solution. So that was our introduction to differential equations. Thanks for watching, and we'll see you in the next video.